over the past 2 days, we've heard a lot about data science and machine learning and analytical workloads. I'm going to flip the script here and close out with a talk about large-scale transactional workloads and the systems that make them possible. I saw Frank McSherry's talk earlier today about Materialize, and he had a little red square at the time, kind of at the bottom of the screen, that was supposed to be the RDBMS of his system. That's what we're going to focus on here. So that little red square. Could I get a show of hands for people who have used a transactional database in the past? Awesome. OK, so kind of everyone here. How many people have used a distributed transactional database in the past? Still, a lot of people. That's awesome. So today I'm going to take you on a whirlwind tour of the architecture of one such distributed OLTP database, CockroachDB. And my goal is for people to leave here today with a deeper understanding of the inner workings of these distributed SQL databases. So here is the 3-word pitch for CockroachDB. It's make data easy. And this is actually the mission statement at Cockroach Labs, the company behind CockroachDB. Our thesis is that too much burden has been placed on app developers. Traditional SQL databases have failed to scale horizontally or survive failures or be able to replicate kind of across the world. In today's application landscape, these are kind of requirements for developers. Now, NoSQL came around and offered horizontal scalability, but it gave up transactions and indexes and, in some cases, even correctness, which in turn put the burden right back on app developers. So there's been an emergence of this new class of new SQL databases that promise to bridge this gap. They offer scalability without giving up on consistency. Before diving in, though, first I'd like to introduce myself. I'm Nathan VanBenschoten. I'm an engineer on CockroachDB. I've been working on it for about 4 years, first as an open source contributor and later as an employee of the company. So here's our agenda for the talk. We're going to start at the bottom of CockroachDB's architecture and work our way up. So at the very bottom of CockroachDB is a distributed, replicated, transactional key value store. That's a lot of buzzwords, but we're going to go through each one. The first thing to realize here about this key value store is that it holds keys and values. And these are arbitrary byte strings. But later we'll talk about the structure that higher levels in the system impose upon these keys and values. So CockroachDB uses multi-version concurrency control. And it uses a hybrid logical clock scheme to version these keys and values. So that means that values are never overwritten. They're instead written with a new version, which improves concurrency within the system. And a lot of databases nowadays use this approach. The key value store exposes a single monolithic logical key space. And this key space is ordered based off of key. Here I'm showing just the keys for clarity, but in reality there are values associated with each key, and in fact multiple versions of the value associated with each key. So the ordered monolithic key space is logical, but it's physically realized by breaking up the key space into 64 megabyte chunks, which we call ranges. These ranges start empty. They grow as data is added. They split when they get too large, and they merge back together with their neighbors when they get too small. So conceptually, you can think of CockroachDB as starting with a single empty range and just growing as users add data. Data is placed into these ranges using an order-preserving data distribution. We don't use a hashing scheme like consistent hashing. And this is actually very important for layering SQL on top of this key value store. Because SQL demands a lot of efficient key value scans that are ordered. Within a range, the keys are still ordered on each physical machine using a per node embedded key value store. And CockroachDB uses RocksDB for this purpose. So in order to maintain the ordering between ranges, a range indexing structure is needed. We store the structure inside a set of well-known ranges within the system so that anyone can locate the top of the structure, which ends up looking kind of like a B tree. This provides a two-level indexing structure that's similar to Bigtable, HBase, and Spanner. So the fully ordered keys enable efficient scans of ranges. Here's a depiction of scanning between a dogs table between the names Muddy and Stella. And you can see that we're using the indexing structure to look up exactly what ranges store that span of keys, and then scanning just over those keys. So now that we've talked about how data is organized within this key value store, we can now talk about how reads and writes access the data. To do this, we're going to need to switch gears and start talking about replication. For those unfamiliar, replication means keeping multiple copies of the same piece of data in sync across machines. CockroachDB uses Raft for replication. Raft is a distributed consensus protocol that's similar to Paxos. Now, how does CockroachDB use Raft? Well, each range within the system is its own Raft group. And I'll say that one more time because it's a frequent source of confusion. Every single range within CockroachDB runs its own Raft consensus protocol to keep its portion of the key space in sync across multiple replicas. We don't replicate at the level of nodes. We actually replicate at the level of these ranges. And by replicating at the level of ranges, we're able to get fine-grained control over data placement across the cluster. The distributed consensus algorithm provides a very useful building block for our key value store, that being atomic replication. Commands which change state are proposed by a leader, distributed to followers, and only accepted when a quorum of these replicas acknowledge the request. So in Raft, a quorum means a strict majority. Here we see that we have 3 replicas holding the same pieces of data. When a write comes in, it's distributed to all 3 replicas, and only once 2 out of the 3 replicas have written the command to disk is it acknowledged to the client. And this means that even if some of the nodes here fail, the write will still be present in the system. So this is an important part of CockroachDB's resiliency story, as it means that we can lose machines and still stay online. So quorum replication is reasonable for writes, but it's actually fairly expensive for reads where no state is changing. Consider this example of reading a key from our dogs table. Using a consensus read would mean we would have to go to all 3 replicas, wait for a majority to respond, and piece together the response to determine what was the consistent state across the replicas. This would slow down the reads and impose extra network traffic throughout the cluster. It would be pretty nice if we could just go to a single replica, ask for its local state, and return that to the client. But we can't just read from any replica because that replica might be behind. It might not have the latest state for a given key. Yet the replica that coordinates these writes, which I've called the leader so far, but we're actually going to call the leaseholder from this point on, is always aware of what writes have been committed. So it can service reads without communicating with other replicas in the system. So we say that the leaseholder has the range's lease. And these leases give CockroachDB consistent reads without consensus. In addition, the leaseholder implements some of the concurrency control mechanisms used by transactions, which we'll talk about later. These include key range locking and deadlock detection. So I said that data in CockroachDB is stored in ranges, and these ranges are replicated, and they can be stored across any nodes in the cluster. So where do we put the replicas? Well, this is the replica placement problem. And there are 4 signals that CockroachDB uses to determine where to place replicas. In the interest of time, I'm going to skip over the first heuristic here, because it can be summed up as we try to balance space utilization across the cluster, We don't want any one node running out of space. So let's start with diversity-based placement. For a distributed system, diversity improves availability when replicas are spread across failure domains. Failure domains are any unit of failure, such as a disk, a single machine, a rack, a data center, or even a region. For obvious reasons, we wouldn't want to store the same piece of data on the same disk, because if that disk went down, we'd lose both copies. So CockroachDB attempts to spread replicas across as many failure domains as possible while adhering to admin preferences for where that data can and can't be. Now, the next heuristic for replica placement is load. You might imagine that spreading out the space usage across the cluster would be enough to spread out load, but that's not really the case. For instance, I said earlier that the reads are only serviced by leaseholders. So if we put all the leaseholders on the same node, then all of the reads would be going to that one node. And we'd have a huge imbalance in CPU utilization and network traffic. So the first mechanism here is to spread out leaseholders across the cluster. Unfortunately, load isn't evenly distributed across the key space either. For instance, in this slide, the blue range here has a lot higher load than the rest of the key space. And we see this in practice all over the place. Customers often have reference tables that are accessed on every single query. And those tables end up being a lot hotter than the rest of the system. So CockroachDB tracks per range load metrics and then balances load for those ranges across the cluster. In this case, we see that the blue range ends up on its own nodes because it's accessed so frequently. In practice, there are thousands of ranges per node, but this heuristic is still very important. And the final heuristic that is used to determine where to place replicas is latency. So the distributed key value store is actually a geo-distributed key value store. And the geo part is very important here, because geographic latencies can be very significant, from tens of milliseconds for small hops to hundreds of milliseconds for large hops. So CockroachDB implements two mechanisms to place data where it's needed. The first is a manual mechanism, where a user can specify, for instance, that all of the replicas for a range must reside in one locality. Or they can specify that the leaseholders for one range must be in some locality. For instance, they might specify that the leaseholders for all ranges containing California users' data must remain in California, because that's where it's being accessed. The other mechanism is automatic. CockroachDB attempts to move leaseholders and replicas close to where they're being accessed from. So this is called follow the workload. And it allows Cockroach to automatically move data to where it's being accessed and adapt to changes in workloads. So moving up the stack, the next thing we'll talk about is transactions. I said this was a transactional key value store. Cockroach implements serializable isolation. And the topic of isolation levels are confusing but fascinating. It's a very deep topic, and yet serializable isolation is kind of easy to think about. It's fairly intuitive. Concurrent transactions behave as if they were executed in some serial order, and there's no interleaving of operations between them. So again, this goes back to making data easy. These transactions in Cockroach can span arbitrary ranges of keys. They can touch the entire key space if they want to. And they can be accessed using a conversational interface. This conversational interface is important for SQL because applications often will start a transaction, read some data, manipulate it in their application, and write it back, all within the same transaction. So let's dive into the implementation of transactions briefly. Transactions provide a unit of atomicity. They're all or nothing. They either succeed or they fail altogether. And transaction-level atomicity in CockroachDB is bootstrapped on top of range-level atomicity provided by Raft. Each transaction has an associated transaction record, and updates to the transaction record are stored on a single range. So we're able to indirect through this transaction record to provide atomicity for the entire transaction. I'll walk through a simple example. And here we have an insert statement. It's inserting 2 rows into a SQL table, which is backed by a 4-node cluster. The insert statement is inserting 2 dogs into our dogs table. And the SQL execution layer will turn this into a series of key value operations. In this case, we're writing the keys Sunny and Ozzy inside of a single transaction. The first thing that a transaction does when it begins life is it creates its transaction record. And it will store this on the first range that the transaction writes to. The transaction record really only has one piece of information, just the status of the transaction. Here, it begins its life as a pending transaction, and later it will move into either a committed status or an aborted status. So each write that a transaction performs while it's running is called a provisional intent. The intents are tagged with the transaction's ID, and if another transaction encounters one of these intents, it has to hop over to the transaction record to determine whether that intent should be visible or not. So we see that both the transaction record and the intent on Sunny are replicated amongst this first range here. And because we're using Raft, we wait for a majority of replicas to acknowledge the change before continuing on. The SQL layer then moves on to writing the second key, which might be on a different range than the first key. So it goes to the leaseholder for this second range, the range in blue, and inserts an intent on Ozzy. And again, the leaseholder proposes this to its followers, and followers acknowledge. Finally, the SQL gateway, which is the node processing the SQL, commits the transaction, which involves going back to the transaction's record and marking it as committed. This operation is again replicated for durability. And when that's complete, the transaction is considered committed. So the SQL gateway can go back to the client and say, your transaction is complete. It can acknowledge the client. And finally, the background process cleans up intents so that reads of them don't need to go visit the transaction record. But note that even if it didn't succeed in time, if it didn't clean up these intents in time, reads of these intents would go to the transaction record, find that the transaction is committed, and treat the intent as if it was committed. So I've talked a lot about keys and values, but CockroachDB is a Geo-Distributed SQL database. So now it's time to talk about SQL. Cockroach implements the SQL that you're familiar with, kind of standard SQL, from schemas to indexes to transactions to foreign keys. The dialect of SQL that we implement is actually exactly Postgres's. And the wire protocol that we speak is exactly Postgres's. So your client application thinks it's talking to a Postgres database when it's talking to CockroachDB. The goal here is for users to be able to pick up Active Record or Hibernate or whatever tools they're used to using and plug them right in without missing a beat. So I'm sure most people here are familiar with SQL. SQL is declarative in that you describe the results you want and not the steps for how to return those results. And this is important as it provides a tremendous amount of flexibility within the implementation of SQL. But that is also a large burden for the SQL database implementers. SQL is tabular, and tables are composed of rows and columns. The columns are defined in a schema, and these columns have types, like float or string. Tables have optional indexes that provide efficient lookup into the table. And they have foreign keys to enforce referential integrity. But wait a minute. I said SQL data has columns and types, and yet we've talked only about untyped key value pairs. This seems rather distant. But it turns out it's not too distant. We can map SQL directly onto key value pairs without all that much work. And we'll see how. Let's start with a basic table here. In Cockroach and in most SQL databases, every table has a primary key, which is just a special index that's required to be unique and required to store all of the columns in the table. Each row in the primary key maps directly to a single key value pair. And each row in a secondary index also maps just to a single key value pair. For each index, the indexed columns are encoded into the key of the KV pair, and the non-indexed columns are encoded into the value of the KV pair. We can see this here. You can probably imagine a scheme for encoding the value here. We could have used protobufs or Avro or any other encoding scheme. In practice, we chose to do our own encoding for performance, but it doesn't really matter. What matters much more, though, is the encoding of the keys. We need an encoding such that the encoded key is ordered the same way that the logical columns they encode are. So with our inventory table here, we need the encoded ID column to be encoded with the same ordering as what we logically consider integers. So people here might be able to come up with an encoding that would work for that requirement. And I'm just going to gloss over the fact that it actually is possible to do this with arbitrary tuples. So we can do this with arbitrary data types and arbitrary tuples. We didn't invent this idea, but we use it heavily during this mapping from SQL to key value stores to key values. So Cockroach supports multiple tables and indexes by just prefixing each key with the table and the index name. So this is what it looks like for an inventory table here. But SQL is a lot more than just table data storage. SQL is a powerful query language. And since Cockroach is a SQL database, we need to implement that query language. I'm going to go through a quick overview of how basic SQL query execution works before diving into distributed query execution and finishing up with a mention on query optimization. So SQL has a relatively small number of basic relational operations. It has projection, selection, aggregation, and joining, and just a few more. These are expressed in SQL via constructs like select, where, group by, and join. These relational operators are part of relational expressions. And a query tree or a query plan for a SQL query is just a tree of these relational expressions pieced together. And executing a query plan just runs these operations to completion. So I'll give a brief example of how SQL query execution works with this statement here. Here you see we're reading from an inventory table and filtering on the name column. So what this looks like under the hood is that we start with the scan. We start with the source of the data. And we pass this through a filter operator. So we're filtering based off of the name of each row. The resulting filtered rows are projected out to just show the columns that are desired here. In this case, just the name column. And that result is returned to the client. So it's all actually fairly straightforward. But here, it's actually fairly inefficient as well. People might have picked up on the fact that we're performing a full table scan here. We're scanning over the entire inventory table before we're actually filtering at all. And without more information, that's really all we can do. But what if we had an index directly on this name column? Well, if we had an index on the name column, we could scan a contiguous set of keys and perform the filtering right there in the scan. We could push the filter into the scan itself. We'd still have to project out the name column, but this is a fast operation. And then we would just return the results to the clients. So the decision to use such an index is called a transformation, and it's performed by the SQL optimizer. I'll dive into that shortly. At a high level, these relational operators are straightforward, but there are still two fairly large challenges we have to deal with. The first here is correctness. User-defined schemas mean that there's a lot of generality involved in SQL, and that results in a lot of bookkeeping. And making that bookkeeping fast is tricky. And that leads into the second challenge here. We need to make this fast. Users expect SQL execution to be performant. Now, there are three tactics that we use to make SQL performant. The first is fairly straightforward. We try to write tight, well-written code that doesn't allocate during individual rows, and it doesn't waste a lot of CPU. The next tactic is something that most SQL systems will do, where we specialize operators to specific scenarios. For instance, a general purpose group by operator needs to handle inputs that are unordered. And it typically does this using a hash table. But if the input is ordered, then often we can skip the hash table entirely and just stream the results back up. Lastly, being a distributed system means that we can distribute SQL execution entirely. So we're a little short on time, so I'm going to skip straight to this last point. With a geo-distributed database, network latencies and throughput become very important considerations. And with a distributed SQL execution, we're able to push fragments of computation as close to the data as possible to avoid these slowing down queries. Let's look at an example of a SQL query that's aggregating rows using a group by operator. If the table is distributed across 3 data centers, then the query will instantiate 3 processors to scan the table. These processors sit right next to the data that they're scanning. And the output is fed right into a local group by operator. It's still right in the same data center. Finally, the per data center group by operator output is fed back to a single final stage, and that's what's returned to the client. So this reduces network usage over these wide area network links, and also offers an opportunity for parallelism, which is beneficial even when you're running a system like Cockroach within a single data center. So moving on to our last topic, and I think we are short on time. So I said that SQL queries are declarative, and that it's up to the SQL database to decide how to execute them. And this ends up being the job of the SQL optimizer. So there can be a lot of logically equivalent plans, and it's up to the optimizer to choose which one to run. Now there are 4 stages here to running a query. We start by just parsing the query and turning it into an abstract syntax tree. Next, we prepare the query by folding constants and checking types and doing a lot of preparation work. Finally, we use a cost-based optimizer to search through the different transformations that can be possible on this query to decide if there are any better query plans that could be made. And then we pick the lowest cost query to run. So that was an overview. But when it comes to SQL optimization, there are actually 2 types of query transformations. There are cost-independent transformations and cost-dependent transformations. I'll start with the first one here. So cost-independent transformations are transformations that always make sense to run on a query. And again, we're searching for the best query plan to run. So we always want to run these transformations. An example of this is to fold constants before we actually run the query. We don't want to be doing this per row, so we want to do this ahead of time. Now in Cockroach, these are all defined in a custom DSL, and the DSL allows us to match against patterns within a query plan, and then perform the transformation right in line. There's also another set of transformations that aren't universally good. Some of them produce faster query plans, and some don't. Internally, Cockroach calls these exploration rules. because they're exploring the set of logically equivalent query plans. So how do we decide whether to apply one of these rules if they're not always good? Well, we actually always apply them, and then we store both the pre- and post-applied version of the query plan. So if you're thinking that that could get expensive fast, then you're right. But this memo structure allows it to be kind of feasible to do this. And then we use table statistics to estimate the actual cost of each of these query plans. So I'll give a last example of what this looks like. I'm going to skip there. Here we have a query that's scanning over table A, filtering based off of a column X, and then ordering based off of a column Y. And the question is, what query plan do we choose to execute this query? The initial AST gives us something like this, where we're just going to scan, filter, and then sort. And this is pretty basic, but this would work. If we have an index on column X, then we can push the filter into the scan. And we saw this earlier. And this would speed up the execution. And if we have an index on Y, we can use the ordering in the index to avoid the sort. So this, again, could speed up execution. But it's unclear which of these last two query plans are better. It really matters how many rows are passing between each stage of this query plan. So for instance, if filtering brought us down to just 10 rows, then the scan would be very fast. So we'd want to choose that. Sorting 10 rows is very quick. But if filtering left us with half of the rows, then we wouldn't really save much by using the index on X. However, we would avoid the entire sort if we use the index on Y. So we'd actually want to choose that one. And we really can't know ahead of time which one will be better, but we can use table statistics to get an estimate for what one will be better, and then pick the cheaper plan. So something that Cockroach does, because it's distributed, that most systems don't have to deal with, is that it actually takes locality into consideration in its cost model. So just like we were using table statistics to determine which query to run before, Cockroach actually uses the locality of the data that's scanning to determine which query plan to run. Here I've defined a table called postal codes that has an index on ID, its primary key, and actually has two different indexes. It has 3 different copies of the data in all 3 regions within the world. This is a typical reference table that foreign keys might be pointing at. The optimizer is able to use the locality of the different indexes to determine which of these indexes to run queries against to avoid wide area network hops. And this is a simple example, but the mechanism is general, and we get a lot of use out of this. So let's review. Internally, Cockroach contains a distributed, replicated, transactional key value store. The KV store exposes a monolithic key space that's physically broken down into 64 megabyte chunks. Replicas within these chunks can be placed on any node, and a set of replica placement heuristics determine where to place these replicas. Tabular SQL data is mapped onto this key value store. SQL execution is a lot of bookkeeping, along with a heavy dose of performance. And distributed SQL execution moves partial SQL execution as close to where the data resides as possible. SQL optimization attempts to find the best execution plan for a logical query. And locality-aware SQL optimization recognizes the importance of latency in determining the best SQL execution plan. And that's really it. So at this point, you've kind of all walked through all of the architecture in a distributed SQL database, and you're all certified to go build a SQL database. So congratulations.
Hi, thank you for this deep dive into database architecture. It's great. Could you comment on how CockroachDB fits into big data ecosystem what are the potential alternatives that you might be replacing because of the benefits you offer versus other tools that may be in the sort of more complementary, for example, like analytical databases or SQL engines, right? Mm-hmm. How like things like, I don't know, Presto would interact with CockroachDB.
Yeah, that's a great question. So CockroachDB is definitely focusing on OLTP use cases. And so there's still a big need for an OLAP system often to sit alongside one of these OLTP databases. So we work with tools like Snowflake DB to kind of stream changes from Cockroach straight into analytical databases. There is work to make kind of light analytics work within Cockroach, but it's not designed for that tool. Yeah.
How does Cockroach deal with gateway failure during a transaction?
Yeah, so typically deployments of Cockroach will have a load balancer out in front. So you'll be balancing SQL to different nodes in the cluster. But if your gateway fails while you're executing a transaction, that transaction will be killed and it won't complete. But the client application will get an error and it will just have to retry on a different gateway.
So you mentioned that Cockroach collects a memo of all the possible query execution plans and really like runs through and iterate on it and figure out how long it should take. Mm-hmm. How does that memo feed into the query executor on top of statistics? Because based on the example you provide, it looks like statistics is more around number of records in this range and things like that.
Yeah. So I think I mentioned statistics twice in this talk. One was about load on a range, but we also keep kind of per column and per table statistics, which work just like a traditional cost-based optimizer. So within the memo, we'll be pruning plans based off of the expected number of, kind of the expected cardinality that we expect throughout a query plan.
I see. So you don't actually track the actual, but you mentioned that, so the third kind of metrics that you track is actual query execution time.
Yep.
Does that feed back into the statistics?
Right now, that doesn't feed back into the statistics now.